So this is probably the biggest portion of the object-oriented unit. So as such, I'm going to break it up into a couple videos just to kind of reduce it. Otherwise, you're going to be watching like an hour and a half long video, and that's just simply too much. So let's get started quick. First of all, so our topic of the day is Pillar 1, encapsulation. So what does that actually mean here? So in this case, object-oriented programming is really foundationally built from three pillars. So the first one is the one we're going to talk about right now, which is encapsulation. Then we're going to get into inheritance, my personal favorite, and follow that up with polymorphism. That's probably the most applicable once we get into large complex systems. But encapsulation is really the cornerstone. Now, not all object-oriented programs use all three of these. They all will use encapsulation for sure. However, inheritance and polymorphism are kind of optional. That being said, for a program to be considered fully object-oriented, it would make use of all three of these. So let's get through this. So this lesson is going to focus on encapsulation, as I said. So the term encapsulation really has two meanings relative to object-oriented programming. And it's kind of stuff that we already talked about. The first one is the idea of grouping data and functionality into one package. We've called this package a class. So we wrap it in that nice little bow that is that template, that blueprint. Great. That's the biggest detail. So the idea of grouping data and functionality. The next piece is hiding data and functionality from the outside classes. You don't always want every class to be able to access and manipulate all your information and functionality. We're going to get into a couple examples of why this is important, but that's really the key thing here, right? Sometimes you just simply want some data elements hidden. For example, if you were an object, you would hide your personal information like your health records, your financial records, and something like that. You wouldn't just give that information out to anybody because that'd be dangerous, right? Or your passwords to your programs. You got to keep things secure. So grouping of data and functionality and hiding of data and functionality. So let me give you an example. Imagine that you wanted to withdraw some money from a bank. This is a pretty common operation. Now I'm going to take you back a little bit so this analogy makes a little bit more sense. So let's pretend that it's the early 2000s and everybody doesn't do all of their banking online. So imagine you walk into a bank and you walk up to the teller and you're like, I'd like to withdraw $200. And the teller looks at you. And they don't just hand over money. They don't let you walk in the vault. There's a whole bunch of checks and balances, pardon the pun, before you can even access that money. So the first thing they're going to do is look for proof that you are who you say you are. So that might include something like showing identification or showing your bank card and getting you to punch in your PIN number. So let's say you get through that security check first. The next thing they're going to do is they're going to say, okay, well, let's make sure that you have enough money in your account. So they look on their machine and they're like, okay, you have enough money in your account. Are they going to let you go walk into the vault and get it? No, never, ever. What they're going to do is they're going to go into the vault, they're going to come back out, and they're going to count the money in front of you and then hand it off. At no point do you ever get direct access to their data, their money. You shouldn't, because it needs to be behind that secured wall. So we do the same thing in our programs. Imagine you were creating a program that was modifying shapes, for example. And one of those shapes had the ability to modify the dimensions of your shape. Maybe it was a rectangle and you needed to add in a new length and width. Well, you accidentally add in like a negative length. Well, that's a big problem. That's an impossible shape. So what we would want to do is we would want to limit you. We wouldn't just let you set the length of that shape. We would have some kind of method that you would call, and that method would verify that the data you're trying to change it to is safe, right? Similarly speaking, if you tried to withdraw money from an account that did not have enough, it would fail on that withdrawal. So that's the same idea. So that's the idea of encapsulation. Grouping data and functionality, but more important, hiding data and functionality. We're going to get into how that actually occurs in a moment, but we got to step through this piece by piece. So why do we encapsulate? We encapsulate our data and functionality to improve security, which we just saw, and reliability. Reliability. Interesting. So reliability is the idea that we know that every time we do something that it will act the same way and it will act safely every single time that we use it. So we know how the data is being accessed and what operations are being performed on that data. This makes program maintenance and debugging really easy. It also makes it extremely easy to work between multiple classes and multiple people working on that program. So imagine you were in charge of one class and another person was in charge of another class, but they needed to use some of your functionality. So by you ensuring that the method that they need to use always had the same name and always has very specific parameters that they need to supply, then you can ensure that no matter how you implement it inside, it's not going to affect what they need to do. To them, it's a black box. They're just saying, give me stuff. And then how you go about doing that is up to you. Okay. So I want you to think of encapsulation like how you send a letter in the mail. So imagine you're going to send grandma a happy birthday card and she lives overseas. Okay. And you fill out your little card, you draw a little picture, put a little heart on it, and you put it in an envelope. You write grandma's name on it. My wife's from Portugal, so let's assume that your family's from Portugal, for example. And you put it in the mail. A couple days later, grandma gets the card. She opens it up. She's gushing. She calls you. So, oh, thank you so much for remembering me on my birthday. Really appreciate it. Great. Do you have any idea how that letter got there? No. As far as you're concerned, all you did was take letter A and put it in mailbox B. And a couple days later, it magically appeared in her mailbox. You have no idea how. And you know what? It doesn't matter how. You used the functionality of the post office called deliver mail. You supplied it with an address. You supplied it with a stamp to pay for it. So you gave it everything that it needed to do the job. But you don't care how it actually does the job. You don't know if it went on a boat, if it went on a plane, or if somebody stuffed it in their backpack and started swimming across the ocean. You don't know, and you don't care. It doesn't make a difference to you. Does it make a difference to them? Yes, it absolutely does. So, for example, if they want to take the cheapest route, but they also have to make sure that they're balancing that with speed. Right? Because if your letter takes 6 weeks to get there, you're not going to use that service anymore. Right? No matter how cheap it is, it's not going to be useful to you. So that's the way we want to think about this. We want to think about every time we access functionality from another class, it's a black box. All you know is what you're requesting and what you expect back. You have no idea how it actually operates on the inside, and it doesn't make a difference to you. It's completely irrelevant. Okay. So by using encapsulation, because that's what we're doing here, we're hiding the functionality, we can implement a similar system in our programs. By keeping the method calls the same to the outside source, the inner workings don't actually matter. If we decide to change, let's say, for example, we were creating a program with networking. Well, networking code has evolved immensely over the last 30 years. So it's going to continue evolving. So at some point, your product is going to need to connect to the internet. Well, the way that does it may change, but as far as your program's concerned, you might just have a method called connect to internet, and inside it does the magic. Again, you don't care how, as long as it does it. So what does the structure of an object-oriented program actually look like? Well, most object-oriented programs follow pretty much the exact same structure. The first thing is we have one main class. This is our driver class. So this is composed of objects. It often acts as the driving interface between the user and the functionality of the program. Its core job is to be that layer between the user and your actual program. So the user doesn't ever actually interact with any of your other objects or classes. It only interacts with that driver class, the main class. So for example, you might display like a menu on the screen. It chooses an option. Your driver class would then take the option that they chose, and then it would communicate with the other objects. All right, so it drives the functionality of the program. That's its job, its core job. So for this reason, we call it the driver class. It doesn't actually have to be named driver class. It could be, you could leave it as the default program.cs or game1.cs. It doesn't need to. But its core functionality is to be that interface between the user and the program, and its job is to call the functionality of all the other objects, not to actually do the work, but tell something else to do the work. Think of it like it's delegating the effort. All right, so the first thing is the driver class. The next thing are the objects that are owned by the main class itself. So it can It can also be composed, which can also be composed of more objects. So we saw a couple examples the other day. So for example, you might have a car object. So maybe the driver class, maybe it's like a vehicle rental company or something like that, and it has a whole bunch of vehicles. And each car, the vehicle rental company, the main driver class has a list of cars. And each car, though, is composed of other objects, like wheels, for example. So it maintains its own list of wheels. So you might look like a scenario like this, where the main program owns object 1, 2, and 3, but object 3 also has a connection to object 2. Okay. So we got the main driver class, and we got the object owned by the main class, as well as what they own. Every single object, this is the most important thing of the whole discussion, every single object maintains its own data. And the program-centric data, which is usually very, very little, will be maintained by the main class. So not too much is going to be stored in that main program. Most of it is going to be on the individual objects themselves. It's just really who owns the objects. Okay. So what is the full class structure of, or what does a program look like in terms of a new class? So this is your basic structure. We're going to have a class and then the class name. Okay. So whatever you called your class, it might be class human, class car, whatever. And you have your opening and closing braces. So where does everything belong? Well, as normal, the first thing that's going to be in our program is our libraries, right? So these are any libraries you're going to need within your program, whether that's using system or the collections generic for your list stuff. All that stuff needs to be put up there. Great. Now, if you're building like a mono game project and you're doing games, you may need to include all of those mono game libraries that are in the game1.cs in your other support classes as well. Okay, so every class. The next thing is your attributes. Your attributes are going to be in the global variables. You're like, whoa, Mr. Lane, I thought you said we try not to use global variables. We should be using local. Yes, that's true. But these are variables that need to be maintained for the entire life of the object. Well, that's the definition of global, something that's in memory the entire time. So this is where we're going to define all of our attributes, including the instances of other classes. We may have to instantiate them later, but we're going to define the actual variables themselves right here. Okay, so now we have our libraries, we have our global variables, and right below that is something new called a constructor. Now, if you remember in the previous lesson, we called an instance a constructed copy, something that was built. Let's take another step back. Remember the analogy from the previous lesson about classes being a blueprint, like the house blueprint. Well, that house blueprint never comes into fruition unless you have construction workers to go actually build that copy. Well, that's why we call this a constructor. This is the construction workers. It is you can have more than one constructor in your class, but basically the constructor's job is to be used by other classes to create one instance of this class. This is where you're going to set up all your core data and information and maybe set up some extra functionality. So for example, if this class represented maybe a deck of cards, it was a deck class, it might create all the 52 cards in here, and it may shuffle them as well. All right, so constructor its job is to create all of the needed information and organize everything. So after our constructors, the next piece is a piece called accessors and modifiers. We're going to go into more detail as we go through this, but accessors and modifiers are basically the methods used by outside classes to interact with your encapsulated safe data, right? So this is like basically the bank teller. You come up and say, please give me $200. That would be an accessor. So you're trying to, that would be a modifier because you're trying to modify how much money is in your account. But before you do that, she is going to check to see whether there is enough money in that account, right? She or he, I should say. So accessors and modifiers. So these are used by external classes to access and modify your attributes. Okay. And then finally, the last piece of the puzzle, the behaviors. So these behaviors, sometimes they're going to be encapsulated and completely hidden because they're only meant for use inside. So for example, with that deck That deck example I talked about a second ago, the shuffle method may be just for inside. So it will be completely encapsulated, so it can only be used by this class. Okay. The other classes don't need to. The deck can shuffle itself. But some things are not going to be encapsulated, and you actually want the outside world, the outside classes, to be able to call this functionality, just like they can call the accessors and modifiers. So it might be something as simple as draw a card, which would draw the top card from the deck and return it back. Okay? So, as it says, behaviors are both encapsulated, hidden methods for internal use, as well as methods used for external classes to have this class perform a specific action. So this is the basics. This is the structure we're going to be looking at. So in the follow-up videos, we'll see how many it takes, I'm going to go through and build a program that uses this structure. This is going to be kind of our cornerstone to figure out how this whole program works.